Chapter 13, Section 3 is on partial derivatives. Our objectives are to find and use partial derivatives and higher order partial derivatives as a function of 2 or 3 variables. Now in this chapter, and what you'll see when I handwrite some of the problems, is this symbol that we use for partial derivatives. It's a mathematical symbol derived from the Greek delta. It's used to denote a partial derivative. When I draw it by hand, it tends to look like a number 2. So just keep that in mind as you're going through the examples. This symbol, this partial derivative, is different than the straight d of a total derivative notation. This is a notation that we use for the first partial derivatives. Given a function z, which is a function of x and y, we can find the partial derivatives. We can write them as f with a subscript x, that's the partial derivative of the function with respect to x, and f with a subscript y, that is the partial derivative of the function f with respect to y. Other ways that you can see the same thing is using that partial derivative symbol. It's a partial derivative with respect to x of a function of x and y, or f with a subscript x, or z with a subscript x, or partial of z with respect to x. So keep that in mind. There's many different ways of saying or asking for the partial derivative of a function with respect to x and y. And similarly, you can see in this line here are the different ways that you can represent the partial derivative of a function with respect to y. These partials evaluated at a point you can use this notation here. Now the way we're going to approach finding partial derivatives, if you're given z, a function of x and y, to find f sub x, or the partial derivative of the function with respect to x, you consider y constant and differentiate with respect to x. Similarly, if you want to find the partial with respect to y, you consider x a constant and differentiate with respect to y. And remember, the derivative of a constant is 0. So keep that in mind as we're working through some of these examples. In this example, we want to find the partial derivatives with respect to x and y for the function f of xy equals 3x minus x squared y squared plus 2x cubed y. When we take the partial derivative with respect to x, we're going to treat x as a variable and y as a constant. So keep that in mind as you're working through solving these. Again, if we write the original function, we see that the partial derivative of 3x is 3, the derivative with respect to x. The derivative of the minus x squared y squared, the derivative of x squared is 2x, and y squared we treat that as a constant, so that's part of our derivative. And the derivative of 2x to the third power times y is, using that power rule, 6x squared times y. We're treating y as a constant. So that's our partial derivative of the function with respect to x. To find the partial derivative with respect to y, again, we're just writing the original function over. When we take the derivative with respect to y, we treat x as a constant. The first term, 3x, we treat as a constant, and the derivative of a constant is 0. So that's why you don't see that included as in the partial derivative with respect to y. Now the derivative here, we treat x squared as a constant. The derivative of y squared is 2y. We include that constant. And the derivative of 2x cubed y, this is like taking the derivative of a constant times y, which would be 2x cubed. You want to practice these, get the hang of it and you'll have plenty of practice when you do your homework. Let's find, in this slide, we're looking at the partial derivatives of a function of two variables, and we're looking at a geometric interpretation. So given f of x, y is a function of two variables, we can say z is equal to f of x, y. That represents a surface in space. Now when you find the partial derivative of that function with respect to x, what you're doing is finding the slope in the x direction. Slope at a point on the surface. if you're on the surface and you want to measure the slope, you look in the direction of the positive x-axis and measure the slope in that way. That's our partial derivative of the function with respect to x. You want to find the slope in the y direction, evaluate the partial derivative of the function with respect to y. So we get two slopes at a given point. So in this example, we're going to be finding the slope of a surface in the x and y direction. Our function f of xy equals negative x squared y minus y squared plus 25 over 8. We want to evaluate this at the point 1/2, 1, and 2. Now x is equal to 1/2, y is equal to 1, and then the z is equal to 2. So if you were to plug in 1/2 for x and 1 for y into this function, the output would be 2. That gives you the location. The point is x, y, z. So if we find the partial derivative of this function with respect to x, we have negative 2x squared over 2, which simplifies to negative x. And all of this we treat as a constant, and that derivative is 0. The partial derivative of the function with respect to x is negative x. And the partial derivative with respect to y is negative 2y. We're treating the x as constants when we find that partial with respect to y. And then we find that that is negative 2y. So to evaluate or to find those slopes in the x and y direction, you're going to plug in 1/2 for x and 1 for y. If you plug in 1/2 for x, we see that the partial derivative with respect to x is negative 1/2, and if you plug in 1 for y, you get negative 2 as the partial derivative with respect to y. So the slope in the x direction is negative 1/2. We'll plug that into the partial with respect to x, and the slope in the y direction is negative 2. What that looks like geometrically is the surface. The original function is sketched here, and looking at a point on the surface, looking in the direction of a positive x-axis, the slope here is negative 1/2. And looking at in the y direction, the slope is negative 2. So as you can see, looking in one direction, the slope is much steeper going down than looking in the other direction. Now imagine you're on a hill. If you look up the hill, or if you look in many different directions, you'll see that the slope depends on what direction you're looking. So these partial derivatives give us the slopes looking in those two directions. If we have a function of 3 or more variables, we use similar notation. Suppose w is equal to a function of x, y, and z, then this partial derivative of w with respect to x can be written this way, or using the subscript notation, and the same thing in terms of the partial of w with respect to y and the partial of w with respect to z. Here's an example. We want to find the partial derivative of this function of 3 variables, x, y, and z, equals xy plus yz squared plus xz. With respect to z, consider x and y to be constant and obtain. So if we want to find the partial derivative of this with respect to z, you're going to treat x and y as constants. So the derivative of the first term, x and y, treat them as a constant. That derivative is 0. The second term is yz squared. We treat y as a constant, so we take the derivative to find 2yz. And then the derivative of the last term with respect to z, treat z as a variable, x as a constant. That derivative is x. So that's our partial derivative of the function with respect to z. To find the partial derivative of this function, z, which is equal to, f of xyz equals z sine of the quantity xy squared plus 2z. We want to take the partial derivative of this with respect to z. You consider x and y to be constants. So we have z times the sine of a constant plus 2z. So we use the product rule to find the partial derivative with respect to z. And remember, the product rule is the first times the derivative of the second plus the second times the derivative of the first. So we have the first is z times the derivative of the sine plus the sine of all that times the derivative of the first, derivative of z. So we know that the derivative of sine of any u, or sine u, is equal to cosine u times the derivative of u. The derivative sine of this quantity is cosine of that quantity times the derivative of what's inside with respect to z. You're going to treat z as a variable, everything else as a constant, and that has a derivative of 2. So that's the first times the derivative of the second, plus the second times the derivative of the first. And the derivative with respect to z of z is 1. Now you can simplify this and you can simplify and just clean it up a little bit to get the final answer for the partial derivative with respect to z. For this example, we want to find the partial derivative of f of x, y, z, w. So this is a function of 4 variables, where the function is equal to x plus y plus z divided by w. We want to take the derivative of this with respect to w. You can consider x, y, and z to be constant. So you can use, this is a constant in the numerator divided by w. You can use the quotient rule, or you can write this all as x plus y plus z, all of that times w to the negative 1 power, and use the power rule to get negative the quantity of x plus y plus z all divided by w squared.